Okay, good morning, everybody. Welcome back to the third day of our school. We will start the day again with the 2-hour lectures, and then we will have the labs. Through the lecture time, I will be sending you
third day of our school. We will start the day again with the 2-hour lectures, and then we will have the labs. Through the lecture time.
Sorry.
Okay. It's okay, no worries, perfect. So I will be sending you the new exercises that she prepared for all of you. So be paying attention to your email as well. Thanks, Aurora, for the third day, and welcome back.
Great, thank you. Sorry about that. I had both of my screens talking.
No worries.
All right. Yeah, so today to start the lecture, we're going to be talking about how spectra are made and line broadening mechanisms and how elements make absorption lines, how molecules make absorption lines, and all that kind of stuff. Since the last few days, we've talked about how high resolution spectrometers and spectrographs work. And then we talked about how to reduce the data. So now we can start talking about more of the astronomical applications of the data. So I will share my screen. Great. Okay. Yeah, so like I said, today's lecture is on the basics of spectra. So I'm sure that you have all learned this in your introduction to astronomy classes, but I thought that I would kind of start from the beginning and do a bit of a review on what type of objects make what type of spectra. These are Kirchhoff's 3 laws. First we have a hot, dense source. And if you put the radiation from a hot, dense source through, or optically thick, through a prism, what you're going to see is a continuous spectrum. And the continuous spectrum is going to emit like a black body. So continuous emission with a peak at some temperature and some wavelength. Okay, so next, if you have, again, hot gas, but now the gas is diffuse, so there's not as much of it and it's optically thin. Instead of seeing continuous radiation, you're going to get emission lines at the wavelengths of where the elements or molecules in your gas are emitting. And so that's what this image here is showing. This is our emission spectrum. So we see single emission lines at different wavelengths. And lastly, if we have now a hot, dense source, and then in front of this hot, dense source, or in between us and the hot, dense source, we have a cooler, optically thin or diffuse gas, you're going to see basically the continuum spectrum in the background, but then you're going to see absorption lines now instead of emission lines from the elements or molecules that are in this cold gas, and they'll take away some of the photons at these specific wavelengths. And so these are kind of the 3 types of radiation and the 3 types of spectra that we can get. We can get emission spectra, continuous blackbody spectra, or absorption spectra. So stars are kind of the main thing that we look at with spectra in astronomy, or at least from my perspective, doing stars and exoplanets. And stars are going to emit the 3rd type of spectra. So the center of the star is hot and it's dense. And so it's optically thick. But then you have this region on the outside of the star's atmosphere, that's a bit cooler and it's more diffuse, so it's optically thin. And the continuous light is going to pass through this outer layer. And depending on what elements or molecules in the outer layer, you're going to get absorption lines from photons being taken away, being absorbed by the elements and molecules at these specific wavelengths. So you get this absorption spectrum, where you can kind of see here, you have like a black body spectrum where there's some wavelength where you have the most flux, but then you have these absorption lines kind of built on top of this continuous spectrum. And to go into a little bit more detail about black body or continuous radiation, since this is kind of the basis for what a spectrum of a star is going to look like with the absorption lines built onto this. The spectrum of a black body depends on the temperature of the object. And so for stars, if you have a hotter star, the temperature here is around 18,000 Kelvin. The peak of the black body is going to be at bluer wavelengths. And also at all wavelengths, you're going to get more flux. So you're going to get more light at all wavelengths, but the peak of that light is going to be bluer. So this is kind of a A-type star, or an O or B, OB or A-type star is kind of these bluer stars. So then if we get a bit cooler, the star has a temperature of 8,000 Kelvin. So this is kind of more like sun-like stars, or a bit warmer. So F stars and G-type stars, and they'll look a bit more yellow because the star will peak at yellow wavelengths. And so even though it peaks a bit more in the red, the blue star still has more flux at all wavelengths. And lastly, for the coolest type of stars, these are M dwarf, K and M dwarf type stars. These stars have temperatures of around 4,000 or all the way down to 2,000 in lower temperatures. And these stars are going to look a lot redder because the peak of their black body is going to be at red wavelengths. And so Wien's displacement law shows you, given the temperature of the star, what the peak wavelength will be. And so I like to use the micron version, since microns are easy for both near infrared and for the visible. Okay, so now that we know that stars have absorption spectra, and we've talked about the base of that spectra, which is black body radiation, now we need to talk about how these absorption lines occur. So you can get both absorption lines from atoms and absorption lines from molecules. So atoms are a bit simpler, and this is kind of basic quantum mechanics type of thing, so we won't go into details about all of that. But basically, you can picture an atom with different energy levels, and the electrons sit at different energy levels. And if electron is at a lower energy level, it can absorb a photon and be excited to a higher energy level. And the wavelength of the transition is very particular. So each element and molecule has very specific wavelengths that they absorb at or emit at. And the wavelength of the transition is equal to the Hc divided by the energy of the upper state minus the energy of the lower state. And for hydrogen, you can use a more simple formula where we have this constant here, and then you can just use the energy levels. So the N is the N equals 1 state or the N equals 2 state, and calculate the wavelength of the transition by just plugging in a known constant here. For other atoms, you need correction terms, and it's a bit more complicated. But at least for the hydrogen atom, you can pretty easily calculate what the wavelengths of the transitions are for different energy levels. So what does this absorption look like? Because you're going from one state to an excited state, it results in well-spaced lines. And usually the lines occur in singlet lines, doublet lines, or triplet lines. And so I'm showing you an example of a model. And I'm showing both. Here's a nice doublet. This is the sodium doublet in an M dwarf star. And also there's a bunch of single lines as well. And the reason that you can get doublet or even triplet absorption is because you have some states that have very similar energy levels. So the upper energy level is very similar, and it just has a slight difference due to the slight energy level differences due to the spin of the electron. And so that's how you can get doublet and even triplet states, is when you have very similar energy levels due to this spin energy level. So I won't really go into the quantum mechanics because that's all complicated and that would take many lectures, and we don't have that much time. But those are kind of the basics of how you can calculate the wavelength for absorption from atoms. And now absorption from molecules is a bit more complicated. So for atoms, you're just moving the electron from one state to an excited state. But for molecules, there's lots of different ways that they can absorb electrons. So not only do you have electronic transitions where the electron moves from a lower state to an excited state, but you also have energy levels that have to do with the rotation of the molecule or the vibration of the molecule. And then within those, there's a bunch of different ways that the molecule can rotate and vibrate. So here's an example of water where you get the stretching, and then you can get asymmetric stretching, and then you can also get bending. And all of these are different energy levels. And so that's why molecules have so many more transition lines than elements, because there's so many different ways that these energy levels can exist. Okay, so even just with that simple kind of explanation, we can already start to see why molecules have so many more lines. And so we can kind of see, here's my same picture, and all of these lines are molecules absorbing, the same molecule absorbing, and it has hundreds of lines in a row right here. Whereas the elements, they have single or double or even triplet, but not hundreds of lines in a row. Okay, so to go into a little bit more detail about molecules, often what you see for molecular absorption is you see these bandheads. So here's an example of a real spectrum. This is the carbon monoxide bandhead at 2.3 microns. And this results from the vibrational 2 to 0 energy level. So CO is just two elements together, and so the vibrational energy is when the two elements can move back and forth in their bond. So remember that the wavelength of the transition is equal to hc over the energy of the upper minus the energy of the lower. And so this first initial line here, the deep line, corresponds to the main transition from the 2 to 0 energy level. But you get all of these other lines because of the rho vibrational interaction. So not only do you get a 2 to 0 change in the vibrational energy level, but you can also get lots of different changes between the rotation energy level. So for vibrational energy levels, we use V, I'm using V here, and for the rotational energy levels, I'm using J. So you're going to get a slightly different energy change if you go from the vibrational 2 to 0, if you also change the rotational from 1 to 0, and then a slightly different if you go from the rotation 2 to 1. So even though you're getting the same change in a change of 1 in the rotational level, you're getting a slightly different energy. And so this coupling of the rotation and the vibration is what causes all of these lines. And so this is, right, so you have like 2 to 1, 3 to 2, 4 to 3, and etc. So for all of these lines. And then you also get secondary bandheads for the opposite. So now instead of going from 2 to 1, you can go from 1 to 2, or you can have no J transition. So you have a vibrational transition from 2 to 0 and no change in the rotational lines. And so you can kind of think about in your head how many different lines that would be just by how many different combinations of a rotation going from 2 to 0 with all of the different couplings from the vibrations. Okay, so this is just an example for carbon monoxide for a single rotational transition from 2 to 0. But we also get this same rotational vibrational coupling for electronic transitions for molecules as well. So that's why molecules have so many absorption lines. Okay, and which molecules and elements exist in the atmosphere depends on the temperature of the atmosphere. And this is set by some equations that you might have learned in your introduction to astronomy classes, like the Saha equation and the Boltzmann equation. And so the Saha equation tells you whether an element is ionized or not, or at what temperature the element will become ionized. So if the element is ionized, then it's no longer going to have electronic transitions because it doesn't have it doesn't have the electrons. And then the Boltzmann equation is going to tell you what energy level the electron is in. And so here's a nice plot that's showing the temperature on the x-axis and the fraction, the fraction of hydrogen atoms that are in a certain state on the y-axis. So here we have the n equals 2 versus n equals 1 state. So as we go to higher temperatures, more of the electrons are excited into the n equals 2 state. And then in green, it's showing the fraction ionized. And so right around 10,000 Kelvin, most of the hydrogen atoms become ionized. And so they can no longer have absorption or emission lines. And then in blue is the fraction that are in the n equals 2 state. So we're going to have a peak in that around 10,000 Kelvin. And so that means that around 10,000 Kelvin, you're going to have the most hydrogen atoms in the n equals 2 state. And so if you're looking for in the atmosphere of a star, where you're going to have the most hydrogen n equals 2 transitions, which is also known as the hydrogen alpha or the Balmer series of hydrogen. So the main one's hydrogen alpha line. You're going to have the most of that line around 10,000 Kelvin because that's where the temperature of the atmosphere sets how many atoms have the particular electron configuration that you need to make that line. Okay, so that's for that was for atoms and having atomic lines. But for molecular lines, it's a little bit different. So not only do you need to have molecules in the gas phase, but you also need to have them actually formed and not dissociated. So at higher temperatures, the molecules are going to be dissociated into their constituent parts. So this is showing a phase diagram for water. And you can see that at higher temperatures, water is mostly in the vapor form. And this, I couldn't find a plot that showed water dissociating, but at even higher temperatures, water will dissociate into its constituent parts. So maybe like OH and H. So then in order to have water absorption in your spectrum, you need to have a very particular temperature range. You don't want it too cold because then the water will condense into liquids and solids and you won't be able to see it in the atmosphere. And you don't want it too hot because then water won't even be formed. It'll be dissociated into its constituent parts. Okay, so now we can kind of use what we've just learned about what temperatures different atoms and molecules emit and absorb at, and apply that to stellar spectra. And so this is showing, I have a bunch of different plots. We'll go through all of the spectral types of what the main absorption lines are in the visible for all of these different temperatures. So at the top, we have a B-type star. So B-type stars are the second hottest after O, and they have temperatures of about 20,000 Kelvin. So those are super hot. And just looking at the shape of the spectrum, you can see that it emits a lot more of its light in the bluer part of the spectrum. So the peak of the spectrum is actually even off of this plot. And then the other thing that you'll notice is that the main absorbers are helium, ionized helium, and hydrogen. So for notation, for when we talk about spectral lines, we have the He2 versus He1, and the He2 is the ionized helium. So one of the electrons is gone, and you get a different transition. So in these really hot stars, most of the lines are from hydrogen and helium. Okay, so now moving down to A-type stars, you can see that the spectrum doesn't look quite as peaked in the blue. We're starting to move a bit towards the red, or a bit towards the visible. And again, here, our spectrum is about 8,000 Kelvin. And the main components in this atmosphere are hydrogen. So I've labeled all of the different hydrogen transitions here. And looking at this plot here, we can see that this hydrogen N=2 state is at the maximum right around 8,000 Kelvin, which means that the hydrogen-Balmer series is going to be strongest right around 8,000 Kelvin. So this really makes sense that these hydrogen lines are so strong. That's exactly what we would expect from theory. Okay, so now moving down to solar type stars. At the top, we have an F-type star. These have temperatures of about 6,000 Kelvin. And we still do see pretty strong hydrogen lines, but we're also starting to see more lines in total. So you can see that the hydrogen lines really dominate. There's very few other lines, but here we can see a lot more other lines. We're starting to see magnesium, more calcium, ionized calcium. And then moving down to sun-like stars, we start to see even more lines forming. So more iron, more magnesium. We still do see some hydrogen lines, again, ionized calcium, and a bunch of lines over here in the bluer part. And again, as we're moving to cooler temperatures, just notice that the spectrum is starting to be peaked at at redder wavelengths. And next, for the low mass stars, these have this is a K4 spectral type here, and the temperature is about 4,000. Here's an M2 spectral type. The temperature is about 3,000 or a bit more. And around these spectral types is when we can start to see molecules forming in the atmospheres of the stars. And it's especially noticeable at M star spectral types. So here we can see lots of absorption lines again, lots of metals like iron, magnesium. And down in the M dwarf, you can see that instead of having lots of individual lines, we're starting to see more and more of these broad features. And these broad features are caused by molecular absorption of a bunch of lines kind of really close together that are piling up on top of each other, which this is only moderate resolution. This is only resolution of about 2000. So at this resolution of about 2000, it kind of just looks like one big absorption feature. And so the main absorption feature in the optical spectra of M dwarfs is from titanium oxide. So that's this feature labeled here and this feature labeled here. And also you get a bunch of, besides titanium oxide, you also get a bunch of hydrides. So these are metals paired with hydrogen. So here you can see we have calcium hydride, and over here we have magnesium hydride. And we still do, we don't see anymore the hydrogen lines because the stars are a bit too cool for that. But we do see now more neutral metals, so like calcium 1 here instead of calcium 2 that we saw before. Okay, and now moving to even cooler things, below about 1/10 the mass of the sun, or 0.08 times the mass of the sun, things start to be too low mass to fuse hydrogen. So they're not considered stars anymore. But we still do get these objects. They still do form. And these are called brown dwarfs. So brown dwarfs are have temperatures that are cooler than about 2000 Kelvin. And we found brown dwarfs with temperatures all the way down to about 500 Kelvin, which is, yeah, really cool. And the spectra of these objects look very similar to giant extrasolar planets. So planets that are discovered, giant planets that are discovered with the radial velocity technique or direct imaging, you can take spectra of them, and these giant planets look very similar to brown dwarfs. So at these temperatures, not only do you get molecules forming, but you also get clouds forming. So you can get some really interesting cloud species like magnesium silicate clouds and iron clouds, and things that it's way too cool on Earth to form. But on these planets, since they're still can be up to about planets and brown dwarfs, up to about 1500 Kelvin, you have some really cool chemistry going on. And the spectra of these brown dwarfs and giant planets are dominated by absorption from methane and water. So here, this is kind of it's a slightly different spectral region. So it's about from 7,000 to 10,000 angstroms. But you can see, even at 7,000 angstroms, we're barely getting any flux for the coolest objects. And it's not until about 1 micron or 10,000 angstroms that we start to see any flux. So again, from black body radiation, we know that these objects must be really cool if we're barely seeing any flux all the way out at 7,000 angstroms, which is already at the very red end of the optical. And the way that we have designated spectral typing of these brown dwarfs is we've added 3 other spectral types, L, T, and Y, for these objects. So you can see here, this object is labeled a T0, we have a T2, and all the way down to a T9. And the main features, like I said before, at the hottest end, you see a few neutral metal lines, but then those disappear as we get cooler, and all of the absorption features are from molecules. So here is methane, and over here is water. Okay, and the last type of object that I wanted to talk about as we get even cooler are the spectra of terrestrial planets. So in the solar system, that's kind of the only place that we can take spectra of terrestrial planets so far. Here are the spectra of Mars, Venus, and Earth. And here you can see the real difference between them. So Venus, you can see here they've labeled, this is all carbon dioxide. So Venus has a very carbon dioxide rich atmosphere, whereas Mars has very few spectral features. So the atmosphere is pretty weak, and we do see a little bit of water and a little bit of carbon dioxide. And then here we have Earth, so they have both a cloud-covered Earth and the average, disk-averaged Earth in blue. And you can see that the Earth's atmosphere is very water-dominated, as we know, and there's some oxygen features and some ozone features. And so these planets are going to, terrestrial planets have atmospheres that look really different from giant extrasolar planets, because instead of being dominated by hydrogen species, they're dominated by species of heavier elements like oxygen, carbon, and nitrogen. And so that's why we see more of these carbon dioxide features and less of the methane features on the terrestrial planets than on the giant planets, and also has to do with the temperatures. Okay, so this is my one slide where I try to talk about the spectra of galaxies, because I'm not an expert on the spectra of galaxies, but I just wanted to show some galaxy spectra to show that you can do a lot with spectra of galaxies, even though it's not my area of expertise at all. But galaxies are basically just the addition of lots of different spectra together, and plus gas and dust. And so in red, here there is plotted the spectrum of an elliptical galaxy. So elliptical galaxies are kind of the old red and dead galaxies, they call them. And so you can see that the spectrum of this red galaxy looks very similar to the spectrum of an M-dwarf star. Let's go back. Okay, here's our M-dwarf star. You can see that it has a lot of the same absorption features, because the main stars that contribute to the spectral energy distribution, or the spectrum of the composite galaxy, are M giant stars. And so there's very few high mass main sequence stars left, because these galaxies are not undergoing active star formation. And on the other hand, in blue, here's a starburst galaxy. And you can see that our starburst galaxy here looks much more similar to either an A star or a B star or something like that. Because A stars and B stars, they're so hot, and so their spectra are so, and they're so bright. And so if you have very many A stars and B stars in the galaxy, their light is just going to completely dominate the spectrum. And these stars don't live very long, and so you can only see them when there's active star formation going on. And so if you have active star formation, the galaxy is going to look a bit more like a or B spectral type, whereas you don't have active star formation, your spectrum is going to look a lot more like a M star. Okay. Great. So now we've kind of gone through what spectra of stars look like, what spectra of brown dwarfs look like, why you get absorption lines, what type of atoms and molecules you expect to have the absorption lines. And so I thought next we would kind of talk about what sets the shape of these absorption lines. Because in this figure here that I've been showing a lot, you can see that there's a very different shape between, here we have the sodium doublet, and here we have absorption from a different atom. And so line broadening mechanisms are really important and can tell us a lot about the physics of what's happening in the star. And so measuring line broadening is one of the best applications for high resolution spectroscopy, because you need that really high resolution in order to see the difference in the line strength between something like this and one of these thinner lines. Okay. And so I thought I'd kind of go through some of the main line broadening mechanisms and tell you where they're important and show you some spectra that have these different line broadening mechanisms. So before we start with anything that's physical to the star, it's important to remember that the broadening of the instrument sets the minimum width of the spectral line. So the wavelength spacing of your instrument, the resolution of your instrument is going to set what, how broad you can actually resolve a line. If you remember from before, we had plots with low resolution, and you can't see basically the line shapes at all. And as we get to higher and higher resolution, we can start to pick out the line shapes, because the broadening of the spectrograph kind of sets what we can see. So then we'll talk about natural broadening, pressure broadening, thermal broadening, rotational broadening, and Zeeman broadening. Okay, so the first thing I wanted to say was natural broadening. Natural broadening usually isn't an important source of broadening, but it's an important concept for pressure broadening later. So natural broadening is just a consequence of the Heisenberg uncertainty principle. And so the Heisenberg uncertainty principle says that you can't exactly know the energy and the time at the same time. So the change in energy times the change in time has to be greater than h over 2 pi. And so what this means for energy levels and energy transitions is that a state with a short lifetime, so if the lifetime of the state, so this delta t, is short, then the energy level cannot exactly be known. And so there's some uncertainty in this energy level. And that creates a broader emission line, because there are a bunch of different energies within this uncertainty that the energy level can have. And so that leads to a bunch of different transitions and a bunch of different wavelengths that are almost the same, but not quite the same because of this uncertainty. The shape of this uncertainty and the shape of the spectral line that will arise from natural broadening is Lorentzian. And like I said before, natural broadening is usually smaller than the instrumental resolution, so it can be ignored. But it's important to know this concept, because we'll talk about it again for pressure broadening. And then quickly, before we go over anything else, we're going to be talking about two different shapes for line broadening profiles today. So we're going to be talking about Lorentzian shapes and Gaussian shapes. And so the difference, there's a Lorentzian and a Gaussian plotted here. And the difference is in red, we have the Gaussian. So it has much narrower wings, but a wider peak at the center. Whereas a Lorentzian has a narrower peak at the center, but much wider wings. And so in order to differentiate between all of the different mechanisms of broadening, we can use the shape of the broadening to say, oh, well, this line looks like it has a Lorentzian shape, so this means that this line is probably pressure broadened. Or this line has a more Gaussian shape, and so that means that the dominant broadening in this line is some sort of Gaussian process that leads to a Gaussian line. Okay, so now pressure broadening is actually a broadening that we can measure in the spectra of stars, and it's related to natural broadening. And so if an atom is in an excited state and it collides with another atom before it spontaneously decays, that collision time will induce a much smaller lifetime. And like for natural broadening, a shorter lifetime leads to a larger energy uncertainty. And so and so because collisions cause it to stay in those excited states for a shorter period of time, there's a larger uncertainty on the energy. You can kind of think of it as collisions are perturbing the energy level slightly. And so here's a real example of differentiating between different types of evolved stars based on the pressure broadening of their hydrogen lines. So here in the top, we have a white dwarf, and white dwarfs are extremely compact and extremely dense. So they have extremely high pressure environments. And you can see that the lines have a huge shape. And then further down, we have a horizontal branch star, which is a bit less dense than a white dwarf, but it's not as diffuse as what we have below. This is a horizontal branch star, so this is a giant star. And so giant stars are puffy, and so you can see that we get even less broadening, and so we get the smallest lines here for the giant star. Okay. And so next we have thermal broadening. And thermal broadening is just caused by Doppler shifts. So any particles that are in the gas, the atmosphere of the star, are going to have a random distribution of motion. And that random distribution of motion is going to be given by the Maxwell-Boltzmann distribution, which depends on the temperature. And so this is the formula for a Doppler shift for a wave. And so you can see that the wavelength will change according to the velocity. So if you have some particles moving this way and some particles moving this way, some moving towards you, some moving away from you, the particles that are moving towards you are going to have light that is blue shifted. So any wavelength of the transition is going to be blue shifted. The light is going to be blue shifted versus the absorption line for the transition of a particle moving away from you is going to be red shifted. So that's what's showing here. Red shift is for something that's moving away from you, and blue shift is for something that's moving towards you. So together, combining the shifts from thousands, millions of molecules, and each of them has a random motion, you're going to get an overall broadening effect. And the broadening effect for thermal broadening is given by a Gaussian. Okay, so rotational broadening is basically the same concept of thermal broadening, except for it's not random motions. And so, before we move on, thermal broadening is important in stars, and it kind of oftentimes it sets the base level of the broadening of the line. And then if the star is really dense, you can get pressure broadening built on top of that. But kind of the base level of the line is often set by thermal broadening. Okay, so now rotational broadening. So thermal broadening, like I said before, is all of the random motions of the star, where rotational broadening is the exact same concept, except for it's for bulk motions. And so the star is a point source. We cannot resolve one side of the star from another side of the star. And so when you combine the part of the star that's moving towards us and the part of the star that's moving away from us and the part of the star that's not moving at all towards us or away from us, you get a broadened line shape. And this also depends on the rotation axis of the star. So you're going to get the largest rotational broadening, which is also known as V sine I, so velocity times the sine of the inclination, for a star that has a rotation axis that's perpendicular to our line of sight, because that means that all of the motion of the star's rotation is either towards us or away from us. It's perpendicular. So you're going to get a small rotational velocity, both from a star that is spinning slowly. So if the star is not spinning as fast, you're going to get less of a red shift over here and less of a blue shift over here, even if the line of sight is perpendicular to us. But you're also going to get a small rotational broadening if the rotation axis is along our line of sight, because even though the star is moving very quickly, none of it is towards us or away from us. And with the Doppler shift, we can only resolve shifts that are in our line of sight, so towards us or away from us. We can't resolve anything that's tangential to our line of sight. Again, because this is Doppler shifts, it results in a Gaussian profile. And so here's the same image that I showed before, except for now I'm using it to, instead of demonstrating just the band head, I'm showing a spectrum in black that has a large V sine I, and a spectrum in red that has a small V sine I. And again, this is the carbon monoxide band head at 2.3 microns. And you can see that the star that has a small V sine I, so either one of these two situations, has much narrower and also much deeper lines. Whereas the star that has a large V sine I has much wider and shallower absorption lines. So yeah, you can see the shallower, so they're not quite as deep, but they're also wider. And so by using high resolution spectra, we can actually, so at low resolution, this would kind of just look like one giant feature. But at high resolution, we can actually see the difference between all of these individual lines. And so we can actually measure the rotation velocity of stars modulated by the inclination. And this is another really great application of high resolution spectroscopy, is measuring rotational broadening.
Hi, Aurora. Sorry to interrupt. You have a question here.
Okay.
Is how can we differentiate the Doppler effect caused by thermal broadening from that of the motion of the star around the the galaxy center?
Okay, great. Yeah, this is a good question. Let me go back. Okay. Great. So the motion of the star around the galaxy is not going to give you a broadening effect. It's going to give you an overall shift effect. So the whole star, as it moves around the galaxy, will have some motion and it'll have some redshift or blue shift. But these broadening effects, they're a combination of a redshift plus a blue shift, which instead of, if we just had a redshift, then the lines would all just be moved slightly. So you would get these narrow, deep absorption lines, but just moved either to the left or to the right. The reason that it's a broadening is because we have a combination of red plus blue. So some of these photons, some of the photons are red shifted and some are blue shifted. And so the whole line looks broader. It doesn't look like it's shifted one direction or the other. So the motion of the star can be differentiated from the broadening by looking at the difference between the shift versus, the wavelength shift versus the wavelength broadening. I hope that answers the question. Okay, let me know if it doesn't and I can talk more. And so there are other line profiles that you can get from bulk motion. So here, rotational broadening, it's the bulk motion of the star, not random motions of the particles in the star. So another interesting shape that you can get, yeah, okay, good. So another interesting shape that you can get is something called a P Cygni profile. And you can get this from an expanding shell of gas. So what the line profile looks like is you kind of have this straight line, and then you have this dip in the blue shifted part of the line, and then an increase in the red shifted part of the line. And the reason that you get this is, say we have our dense gas in the center, which is optically thick. And then we have an expanding shell outwards, which is optically thin. So we have black body radiation from the center, which is going to give a nice full wide peak. But because this diffuse gas here is moving towards us, only the blue shifted part of that peak is going to be removed. And so the blue shifted part of the peak, we get a dip that's because it's being absorbed by the gas that's moving towards us in an expanding shell. And the red shifted part of the peak is not being absorbed because the gas is only moving towards us along our line of sight. And you can see this exact shape in stellar lines from stars like O and B type stars that have really strong winds that are expanding out from them. And you can also see this shape in spectra of supernova. And again, with high resolution, at low resolution, maybe you wouldn't even see this shape because it would kind of be smeared out. But with high resolution spectra, you can resolve some really interesting shapes and really start to pull out the dynamics and the motions of the system by looking at the combination of broadening plus radial velocity and how they interact. Okay, and this is another thing that I'm not an expert in, but I wanted to put a slide on here about how you can also use bulk motions of galaxies to see interesting shapes of spectral lines. So here is a galaxy that has been resolved, and we're looking at a single line that's being emitted from the galaxy at different wavelengths. So part of the line over here has been red shifted, and over here has been blue shifted. And so if you look at a combined view of what that absorption line is going to, or emission line is going to look like, it's going to look like this double horn structure, which you get from a solid disk rotation of a galaxy. And so I think, again, this is not what I'm an expert in, but I read a little bit about this. And this is kind of one of the evidence that we have for galaxy rotation curves and dark matter comes from the shape of emission lines and what we know about solid body rotation versus Keplerian velocity rotation. And you can kind of resolve that in the shape of the emission lines from galaxies. Okay. And the last broadening mechanism that I wanted to talk about is Zeeman broadening. And so Zeeman broadening arises when you have a magnetic field on your object, and then you get this extra coupling between the intrinsic magnetic field of your element, so the internal spin magnetic field, coupled with the external magnetic field, and you get this extra broadening effect. And the Zeeman effect depends both on the strength of the magnetic field and also this Landé G factor. And so this Landé G factor is a quantum mechanical factor that basically just says how strong a transition from a certain element or a molecule will react to a magnetic field. So this is actually a bit hard to read, but let's see. Okay. So here we have no magnetic field in this kind of simple example. And we have a simple electronic transition from a lower state to a higher state. And so you get a single line. But in the presence of a magnetic field, we get this single line splits into 3 different lines. And that's because you have the spin of the electron, coupling to the magnetic field. So you get a slightly lower energy when the spin and the magnetic field are aligned, and a higher energy when they're anti-aligned. I think. I'll have to think about that. Which way is it, aligned or anti-aligned? But anyways, so you get 3, instead of having a single line, when you have a magnetic field, you get 3 different lines. And how far separated these lines are depends on how strong the magnetic field is. So if you have an external magnetic field that's 0, you get no splitting. If you have some external magnetic field, you get a slight amount of splitting. But the larger the magnetic field, the larger the splitting that you get. And in practice, this is the best way that we have of directly measuring magnetic fields on stars. So here are some examples from a paper about measuring magnetic fields on M-dwarf stars. And some of these, so you can see here, this is FeH, this is iron hydride molecule. And some of the iron hydride lines are not sensitive to Zeeman broadening, where other iron hydride lines are sensitive to Zeeman broadening. So you get this weird thing where in blue, we have the model that has no Zeeman effect. And in red, we have a model with the Zeeman effect. And then in black, we have the actual data. So you can see that the model with the no Zeeman effect fits the line really nicely here, but then doesn't fit the line at all. And you need the Zeeman effect in order to explain why we basically see no line here, because the line is so broadened. And you can see these are 3 different stars, and they have 3 different magnetic field strengths. Again, here you can see, so this star obviously has the weakest magnetic field because it shows the smallest difference between the model with no Zeeman effect and the model with a Zeeman effect. And again, here you can see that the line, this single line, when there's no Zeeman, starts to split into 2 separate lines when there is a Zeeman effect. And same here. Single line would be if there is no magnetic field, and it splits into 2 magnetic fields. And so you can use the strength of this splitting in order to determine the strength of the magnetic field. And low mass M-dwarf stars are known to have extremely strong magnetic fields. So here they're showing you their best measured magnetic field is 6.4 kilogauss. And to put that number into context, the average magnetic field over the sun is about 1 Gauss. And so this is over 1,000 times stronger than the average solar magnetic field. And even the one that doesn't look like it has that strong of a magnetic field, it has a magnetic field of 3 kilogauss. So in order to actually measure the Zeeman broadening, you need extremely strong magnetic fields. But those type of magnetic fields do exist on M-dwarf stars. And so this is another really cool way that you can use high-resolution spectra in order to determine magnetic field strengths on M-dwarf stars. Okay, and that is what I wanted to go over in this class, and we're just about done. So let me know if you have any questions, or maybe if you don't have questions now, you'll have questions when we come back from the break.
Hi, Aurora. Yeah, for the moment, I haven't seen any other question on the chat. So I guess that we can just go for the break. We will be back in 15 minutes, I guess. I don't know. Yes. What did I do with the schedule? Let me see. At 9:15. Yeah, in 15 minutes we can come back. So it will be at 3:15 your time, 9:15 Colombian time. So,
and I was wondering if it would be okay. I have a bit less lecture today than normal, but a bit more of the practical class. So I guess I basically finished the lecture now, and I wanted to do the Kahoot quiz, but I have a bunch of practical things to do today. So I guess maybe after next class, I don't know, maybe we can move the break a bit earlier or something.
Absolutely, yeah. You just tell me when you finish the Kahoot. We can just move all the schedule a little bit down on the timing, and then
Great.
Yeah, there is no problem at all.
Perfect.
Okay, then see you all in 15 minutes, and then we will finish this first part of the lecture. Thank you very much.
Great.
See you in a while.
Bye.